Right now, NASA is exploring the sun like never before. In 2018, it launched the Parker Solar Probe, which is swooping to within 6.2 million kilometers of the sun's surface, the closest we've ever been. But what if we wanted an even closer look? Our first stop gets pretty hot. At 7 million to 10 million kilometers above the sun's surface, we reach the corona, the outermost layer of the sun. It blazes at 1 million degrees Celsius, nearly 900 times as hot as lava, and it's tens of thousands of times brighter here than on Earth. Now, the probe's heat shield works like a very good mirror, reflecting 99.9% of the incoming light. But we'll need something even better as we get closer. At about 3,000 kilometers above the surface, we reach the chromosphere, the second layer of the sun. See that massive plume? That's called a solar prominence. These loops of gas are suspended by a powerful magnetic field and stretch for tens of thousands of kilometers beyond the sun, and they can reach over 10,000 degrees Celsius. Exactly the sort of obstacle you'd want to avoid when flying a spacecraft into the sun. And the next layer is just as perilous, the photosphere. This is the surface of the sun we see every day. Down here, you'll start to feel pretty lousy. Because the sun's gravity is so strong, a 150-pound person on Earth would weigh about 4,000 pounds here. That's nearly the same as a rhino. If you could land here, all that extra weight would crush your bones and pulverize your internal organs. But if you take a look around, there's nothing here for you to actually land on, because the sun doesn't have any solid surface to speak of. It's just a giant ball of hydrogen and helium gas. So instead of landing on the photosphere, you're going to sink into it. One of the biggest dangers in the photosphere comes from these enormous black spots you can see as you look around. These are called sunspots. They're cooler regions of gas, some as large as the entire Earth. The sunspots are produced by powerful magnetic fields coming from inside the sun, which on one hand would fry your electronics. But more importantly, where a sunspot forms, a solar flare often follows. That's when magnetic fields and superhot gas violently erupt from the surface, releasing as much energy as 10 billion hydrogen bombs. So let's steer clear of those active regions and make our way to the sun's interior. Just beneath the surface is the convective zone. Here, temperatures reach 2 million degrees Celsius. That's hotter than your heat shield was designed to handle. In fact, there's no material on Earth that could withstand this heat. The best we've got is a compound called tantalum carbide, which could handle about 4,000 degrees Celsius max. On Earth, we use it to coat jet engine blades. So, even if we made it this far, we couldn't actually survive down here. But for curiosity's sake, let's keep going. At 200,000 kilometers down, we hit the radiative zone. This is the thickest layer of the sun. It makes up almost half of the entire radius. So we'll be spending some time here, which isn't great because the pressure is at least 100 million times greater than at sea level on Earth. Because it's so dense, there's not much room for light waves to travel, which means down here, it's pitch black. Instead of traveling across the radiative zone and hitting your eye, the light waves slam into electrons and other particles in the plasma, and some even rebound inward towards our last stop, the core. 500,000 kilometers below the surface, the center of the sun makes up nearly a quarter of its radius. Down here, the pressure has risen to more than 200 billion times the pressure at sea level on Earth, pressing the surrounding atoms so closely together that it's about 10 times denser than iron. Plus, it's a blistering 15 million degrees Celsius, making it the hottest place in the entire solar system. Which makes sense. because almost all of the sun's immense energy is produced in the core. That's right, we're traveling through the powerhouse of the sun itself. Now, contrary to popular belief, the sun is not actually on fire. Instead, all that energy is created through a nuclear reaction, which slams hydrogen atoms together to create larger helium atoms and some extra energy on the side. So even if you manage to survive the blistering heat, the solar flares, and the crushing pressure, you now have to climb out of the solar system's biggest nuclear reactor. Let's just say the odds are not in your favor. Maybe our closest encounter to the sun should be on the beach.